For the agenda of today, we're going to talk about the new technique, GWR, the geographically weighted regression. And also for those of you who have looked at our schedule, you might know that, well, I think it's clear because it's probably the last page of the textbook. So this is our last new topic for this semester. So next week we'll spend time to work on the final projects. So basically next week will be, the Thanksgiving week, and the following week we're planning to do the presentations. So I will talk about some of my ideas about the scheduling, but we can, I think there are some flexibility. There is room for change. Okay, so before the GWR, the geographically weighted regression, I want to begin with a quick review because I know, what we covered last week, the regression week, it was pretty intense compared to the previous weeks. And we basically used 1.5 days to talk about the conceptual issues. And hopefully you folks can develop better understandings through doing the GIS, the lab work. And also a quick reminder that I have extended Lab 8 deadline to the 22nd, which is the Sunday, so not Wednesday, so that will also give you some time to participate in the virtual GIS Day event. So you will have until the end of Sunday. And of course, I can help you on the questions on Wednesday and also through email or office hour meetings. Okay, so just a quick review of the 6 checks. Because as you folks know, like you run a model, it's pretty quick. You just plug in all the settings and you click OK, and GIS will just do the process for you and give you a whole large table for you to interpret. And also, sometimes if your model is not very good, you probably have to rerun the model over and over again until you get your better model. It's not the case for the lab. So for the lab, feel free to just send me whatever you get, and just, as long as you know how to interpret the 6 checks. But for your own work, for example, maybe for the project or for your future work, the graduate student who might be using regression, it's very important for you to be able to read the table, and so that you know how to refine your model and just to get a better results or meaningful results, among each, just trying these different variables or refining your data. So I think it will be, if you don't quite remember, I would say you can quickly open up the handout from last time. Let me also, I should be able to get it quickly. I will send you this handout, so that you have some reference here. It's in my last week's folder. Okay, I'm sending you folks the handout again through the chat. And you can grab the file if you don't have the file. Okay. So instead of going through all the 6 checks by order, I want to just give you folks a few questions, just kind of remind you about, the important component here, or some of the tricky points here. So let's just begin with, so I'm going to just give you a few questions, and feel free to unmute yourself to respond or use the chat, whichever way that is easier for you. So first of all, so we know, you can run your regression model, whether it's only 2, between 1 X variable and 1 variable, or 1 variable and multiple X variables. It's just a difference between simple linear regression or multiple regression. So my first question is, what data types are required for regression analysis? That's usually the very first step, or the initial decision you have to make. When you have your data, you have to make sure that regression actually works for the data you have. Or you may have to do some transformation of your data in order for the regression model to work properly. So what data types are required for the regression analysis? So speaking of, the data types we mentioned, there are nominal, ordinal, interval, and ratio. So what data types are required for regression analysis? It's probably not in the handout, but we briefly mentioned the idea last time.
I was going to say interval and ratio, but I don't know if that's right.
Yeah, so Amy and Amy both said it's ratio and interval, and Blake also agreed on the same thing. Yes, it's interval and ratio. So basically, we need numeric values. Essentially, if you have categorical or if you have ranked data, you have to figure out a way to transform your data so that your model makes sense. That's very it sounds basic, but also sometimes because I felt like when you are doing a research, there's so much going on. It's kind of like beyond what you could manage. And sometimes I saw people just quickly run a model on categorical data without thinking about what the data means. So let's just make sure only for ratio and interval data, slow down and think twice before you run the model. Okay, so and also now let's just go back to the table here. So I know there are a lot of numbers, but what is, let's say, what is the slope coefficient for the distance to urban explanatory variable? What is the specific slope coefficient? It's a simple question. I just want to make sure that you folks still remember where to find the information. The slope coefficient for the distance to urban variable. Feel free to also circle things, if that's easier. You can use the annotate. Cool. So yes, so that's the negative 0.002. That's the slope coefficient. Sure. So basically, we're looking for the y-intercept and all the slope coefficient under the coefficient column within the table. So let me also open up so that I can easily clear drawings. Okay, so let's move on to the next question. Feel free to, chime in if you have a question, if there's anything unclear, or if you couldn't find the information from the, from the handout, I can point you to the location. Okay, so my next question is, it can be trickier. So we have three explanatory variables here. So among the three explanatory variables, which one is the most significant explanatory variable? So we have population, we have low education, we have distance to urban center. Among the three, which one is the most significant explanatory variable? Well, many of you chose low education, but my question is, so what about distance to urban center? Andrew, I couldn't hear you. Or is that just me, or?
Yeah, I don't hear anything either.
Anyone thinks it's distance to urban centers? I saw Simone said it's.
Well, the only reason I would think of it is because it's the outlier. So I don't know if being in the outlier makes you necessarily statistically.
So what do you mean by outlier? Like how do you, where?
All right, maybe I think I'm looking in the wrong place because I'm looking at under coefficient. It's the only one with negative values.
So coefficient itself is not comparable, because all the different variables are measured in different ways. So it couldn't really compare the coefficient directly.
Oh, okay. It was the only one with negative values.
Speaking of significance, we have been talking about the p-value, and p-value. So that's really the place we should look at. And also I'm reading, so Andrew, so are you changing your mind, or? Andrew mentioned it has the highest absolute value under the t statistic. So I know, like, under probability, they both report a very tiny little probability. So that makes the decision trickier. However, and also again, like basically in this case, I don't know if you folks remember that, there are two things we need to look at. So basically the Concord statistic, which is the one we should be used to make decision of whether to look at the robust probability or the probability itself. So in this case, the Concord probability, the p-value for the Concord statistic is very small, so which means there are some spatial variations within the data, which means we should be looking at the robust probability. And in this case, the smallest p-value is the distance to urban center. So that basically tells us the distance to urban center is the most significant explanatory variable. And also just basically like what Andrew suggested, you can also look at the t statistics and see which one has the highest absolute value. So the highest absolute value means they're more towards the tail end of the distribution, so which will be more significant, which also indicates a smaller probability. And essentially the probability is derived from the t statistic. So basically you can look at the t statistic, even if it's negative, because the coefficient is negative. But in this case, it has the highest absolute value, so which indicates it's the most significant. So, and also just a quick reminder that when you want to compare the coefficient between the different variables, instead of looking at coefficient, you should be looking at the t statistic, because the t statistic represent the standardized coefficient. That's just because population is measured by number, the count of population numbers, and the lower education is also in the same unit. However, the distance to urban center is measured in feet in this case. So there's no way you can directly compare, like 50 feet versus 50 people. It's not comparable. So to make things comparable, we use the t statistic column, which is the standardized coefficient, and to compare between the different variables. So this is really something I want you folks to keep in mind, because to me, I think so far, like, seeing students doing research, this is the most confusing concept, because whenever we're like analyzing a model, I think it's just somehow, intuitively, we just tend to look at coefficients. However, please keep in mind that the t statistic is what you should look at for comparison. And also, of course, if you read some other research articles, you'll see, the way people interpret the t statistics. Let me just take a look at the chat. Amy had a question. So Amy just brought up a very interesting question. So, so basically, the slope coefficients will change depending on what variables you have. So your model, in other words, your model coefficients are very sensitive to what variables you include in the model. For example, if you only had population, you will see a very different coefficient. So they're all going to affect the overall model. Like basically by bringing in other variables, the general coefficient for the other variables will also change. So that's that's pretty much always the case. Yeah, that's a great question. Okay, so let me see. Okay, so another question is, what is the amount of variation explained by the model? What is the amount of variation in the y variable, which is the Netherlands cost, explained by the model? So you can give me a percentage value. The amount of variation in the dependent variable being explained by the model. Or if you don't quite okay, so I'm seeing some more responses. So essentially, we know, the R squared value or the coefficient of determination, they represent this kind of like amount of variation in the dependent variable being explained by the model. And all of you are correct. So instead of looking at the multiple R squared, we should look at the adjusted R squared value, which is actually the one you use for comparison, because this adjusted R squared value is the R squared value that is normalized, basically removing the influence of the number of variables, because for the multiple R squared, whenever you're introducing a new variable, it's going to increase. It's just going to keep going up, even if you include a totally relevant variable. However, the adjusted R squared value will normalize, basically remove the effect of the number of variables. Okay, so that's great. Okay, so yeah, I think that's pretty much my questions for the review. And also, of course, you can use the handout to look at other components of the 6 checks. For example, for the, we know the coefficient, we went over the probability, and also the Concord statistic will help us determine whether we should look at the robust probability or not. And also the VIF is the indicator of how basically the multi-collinearity, how related you're between your X variables. So ideally, we don't want any redundancy. If you have very large VIF for a particular variable, which actually indicates that variable is redundant, or essentially that variable is already being represented by another variable in the model. So that's something you should deal with. And we should be using the adjusted R squared value and also the JB statistics. The last one will tell us about whether the model residuals are normally distributed. So I would say, because there's so much going on, always use your handout when you interpret the results. Like no one is expecting you to be able to just quickly say 1, 2, 3, 4, 5, 6. Take your time and use your handout, especially on the final exam or you're doing your research. It's okay just to slowly go over each of the checks, even multiple times, and just slow down, make sure you get everything. So that's basically a quick review. And also one of the 6 checks that we don't see here is whether your model residuals are randomly distributed, which will require us to run a global Moran's-I on the model residuals, and then you will be able to read a number. And ideally, it should be random. However, whenever you see a clustered model residual pattern, which is an indicator of you're missing some important variables. For example, if you see a concentration of model residuals in the urban centers, when you compare the urban centers with the rest, maybe the rural or suburban area, that can be an indicator of maybe you're missing population density or some variable that is differentiate between the urban centers and the rest of the surrounding area. So usually in all the 6 checks, they will tell you what is going wrong for you to further refine your model. And oftentimes, more than one check will tell you the story altogether. If you see a variable that is redundant, and very likely you will see the problem in their coefficient, and also you might be seeing the problems with the model residues as well. So they will, if you see one problem, you will likely see 5 or 6 problems. Or if the model somehow passed all the 5 tests, it will probably going to pass all the tests. So so that's just a quick review about the regression. So take your time, and also, Wednesday for the workday, feel free to, if you want to share your results, we can try to interpret your models together. So whenever you're not 100% sure, let's make sure to get things cleared. Okay, so today, once again, we're going to talk about GWR, and that part is actually related to one of the 6 checks here. So just recall this Concord statistic, which is an indicator of whether the relationships vary across your study area, whether there are some spatial variations in your model. So whenever we see a significant, which is indicated by the star, and also a very small p-value in the Concord statistic, is an indicator of your model might be changing across the study area. Even though you're building a global model, but the Concord statistic tell you that there may be more you want to consider. The things may change spatially. So the distance matters in some places, but may not be the same in the other locations, or population could show reverse trend. So today, for the GWR, it's more about a further exploration based on your OLS. So, that's really why we're running both in the same lab. You started with an OLS, and then we move on to run a geographically weighted regression, just because we did find some spatially varying relationships. So we're going to talk about what is GWR. So focus on some of the major components. And I know the chapter you folks read also mentioned, the 2 techniques of you can do resampling to refine your model, or you can apply a spatial filtering. So, given the time constraint of this semester, because we already covered too much, so we're not going to do, the resampling or the spatial filtering part. But, if you're interested, we can also maybe take the work days to try a little bit. But for now, like for the required components, I would say let's focus on the fundamental conceptual issues, and also the, basically the uses and applications. So for the diagram here, again, we're looking at a scatter plot. So the scatter plot is basically showing you the relationship between housing density and housing price in a study area, and actually 2 cities combined together. So, when we look at the whole data set altogether, it does show a positive relationship, a positive trend, although you can see it's quite scattered. However, if we break the whole data set into 2 different cities, we can see the trend kind of get reversed. So instead of one positive relationship across the whole thing, we see 2 negative relationships. And also, that's actually the problem we mentioned last week on actually 2 weeks ago, correlation, the Simpson's paradox. When you break your data down to smaller subsets, you may observe totally different relationships. So this is exactly where you can apply GWR, because the GWR can help you figure out and examine the different spatial relationships across your study area. So essentially, GWR, this is a very special technique for the geographers. Like so far, we talked about correlation and regression for analyzing the relationships between 2 variables, and both techniques are also universal to whomever running a tabular data or just non-spatial. But the geographically weighted regression is specifically designed for geographers and also for dealing with spatial data. So we'll just basically talk about how this works. And first of all, the GWR is used to model this changing relationships across your study area. So what this means, and this actually means you're going to develop a local model for each location. So it's a local form of the regular ordinary least square regression. So what this means is, for example, if you're running a regression model using the 50 states, each of the states will get a different model. That sounds complicated, but I will quickly show you how your results should look like. And also, like there are other things we can do with this kind of analysis. So each state get a different model. That basically means their model coefficients, for example, the slope values for the different explanatory variables and also the y-intercept will change across study area. So for example, if you look at the model fitted for the state of Illinois versus the model fitted for California versus Texas, you will very likely see a different model. Maybe they still show similar patterns or similar trend. However, also likely they don't quite show similar trends. For example, maybe, for example, if somehow we have this population variable, the population may be a positive relationship with the dependent variable in the state of Illinois. However, it could be negative in another different state. So different states, different location, different feature will get a separate model fitted. The model coefficients are going to be different. And of course, the R-squared value, which is the measure of model performance, can also be different. For example, after running the geographically weighted regression, you may realize that the model performance, the model actually performs very well in California, however, not in the Midwest states. So that can be an indicator of, for you to figure out what is going wrong. Maybe you're missing some important variables in the Midwest. So this kind of spatial variation will give you some additional information for you to further look into this problem spatially, and also maybe for you to discover the missing variables, or for you to discover the other ways you can transform your data to improve your model. So the question is how? So we know, okay, like based on the results, you would see a different model fitted for each location, for each state. So apparently we cannot use all the 50 states to fit the model for each location, because if in that case you will get the same model for each location. So how do we get a different model for each state? And to do that, we'll spend some time here. I know this kernel function may look a little abstract. So the idea is actually familiar, because so far we have been talking about spatial interpolation, or the first law of geography, that closer things are more related than things that are further apart. And also we have been talking about the idea of neighborhood and weights. So for all this different pattern analysis that we have introduced recently, the Moran's eye, or the cluster analysis, the hotspot analysis, they always use the idea of you have to define your neighborhoods. So that can be through fixed distance, and then you can define your function to be the maybe inverse distance, or you can define your distance band. So only features within your distance band are considered to be your neighbors. And also you can also model the closer neighbors to have a stronger influence on this pattern analysis than the neighbors that are further away. So it's actually the same idea for running GWR. So basically you just define your neighbors for each state in the state example. For example, in the state of Illinois, you can define the 10 nearby states to be the neighbor of Illinois for fitting the model. And for the nearby states, for example, Indiana will have a higher weights than the other states that are not adjacent to the state of Illinois. Basically, we're using the kernel function here to define the neighbors and their weights for the purpose of the GWR. So the kernel function, essentially that's one of the functions for fitting the normal distribution. And also for those of you who took GIS 2, well, basically now it's renamed to Geospatial Analysis 392. So this kernel function is basically the kernel density, the function applied to the kernel density we talked about. So it's really useful. Kernel function is a very useful function in spatial analysis and statistical analysis in general. So what this means is, just the same idea we talked about. The nearby, the closer neighbors will have a stronger influence on the GWR, on fitting the model than the neighbors that are further away. For example, in this case, we know, if we consider X1, the number 1 to be the target feature, so number 3 will have a stronger influence compared with number 2. So basically the W here means the weights. And also essentially you're defining something called a bandwidth. And the bandwidth essentially is the distance band. So they're just basically using a different set of terminology. So if you increase your bandwidth, which means you'll be including a larger number of neighbors. And if you reduce your bandwidth, which will include a smaller number of neighbors. So that's just how you can define your kernel function, by changing the bandwidth. And essentially, if you're increasing your bandwidth, you're also kind of just generating a more flattened curve. So which means there isn't much difference between the weights. So basically, the difference between nearby features versus distant features can be less significant compared to a shorter bandwidth. But that's something we don't really have to consider, because there are usually, when you run the GWR, there are some predefined options for you. But the essential idea is you run the GWR based on neighborhoods. Again, the same idea. And also higher weights, nearby features, higher weights, distant features, lower weights. But the program will usually handle this for you. So for the kernel function, so like I said, the actual decision making is so much easier, because there are only 2 types of kernels that you need to choose from. You don't have to define like a long list of different kernels with bandwidth, because usually you just only choose from either doing a fixed kernel or adaptive kernel. There are 2 different types. So if we take a closer look between the 2 different types, the top example, basically for the top example, excuse me, it's called a fixed weighting. So in this case, we use the same bandwidth everywhere for defining the neighbors and weights. And essentially, for example, if your bandwidth is 10 feet, and then you're going to apply this 10 feet buffer, or the circular area around each location, and whatever features within that bandwidth, within that little area, will be considered as your neighbor. So that's the first step. And then for the bottom example, if you can take a closer look, you folks can see maybe the bandwidth will actually change by location. So in this case, a smaller bandwidth is applied wherever you have a denser cluster of points, and a relatively large bandwidth is applied wherever you have a sparse cluster of locations. So essentially what this means is, instead of doing a fixed bandwidth, the fixed radius, you apply a fixed number of neighbors. So basically, the bandwidth will change in order to include more neighbors. For example, you define 10 neighbors, and essentially the bandwidth will be adjusted based on the distribution of the points. If it's necessary to increase the bandwidth in order to include more neighbors, it's going to get a larger one. But if it's okay to use a small bandwidth to have 10 neighbors, then they will stick with the smaller bandwidth. And this whole decision, choosing between these 2, and also you might be wondering, like, how do I determine what is the number of neighbors do I use? The decision is actually even easier in ArcGIS and also in R, just in most of this popular program for applying GWR. And also, by the way, I think I made the R tutorial folder visible today. So if you go into our D2L site and enter course library, you will see a new file called R tutorials from previous class. So if you click on that, that will take you to a Google Drive, Google folder that I created with, I don't quite recall how many, but I think I shared everything I have. So feel free to download all the R tutorial if you're interested in getting more information on R later. I think I'm planning to keep the folder open, so it's okay if you come back later. But if you have some space on your drive, I think it'll be probably easier if you just download everything now, so that you keep a copy. So for running GWR in ArcGIS, essentially it's the same folder where we send the OLS, the ordinary least squares. You definitely double click on the tool, and then you'll be filling out this interface. So within the interface, let's just take a closer look. Actually everything stays almost the same as running the ordinary least square model. So, of course, we define the input features, which is your input data file, and you define your dependent variable, which is the Netherlands cause, and you just use the drop-down menu to select a list of explanatory variables. You have the option to choose only one, but you can choose multiple if you're running a multiple regression. So in this case, we're still running the same idea on population, low education, and distance to urban centers. So we have 3 explanatory variables. And after that, you are going to save your output feature class. So, up until this point, it's pretty much identical to running OLS. So the only difference is here, and which is just something we went over just now. So basically, here for the kernel tab, we know there are 2 tabs, fixed versus adaptive. So for our purpose, and also for most applications in general, I do recommend using adaptive, because it will consider the distribution of your data and adjust your bandwidth accordingly to ensure you have a certain number of neighbors. Otherwise, it's kind of tricky for you to determine a distance threshold for your fixed kernel tab, fixed weighting kernel tab. And afterwards, there's also a bandwidth method. So basically, that's how you are going to determine the size of your bandwidth. So in combination, this adaptive and the AICC, so essentially the AICC is another measure of model performance. So in combination, basically we chose adaptive and the AICC to ensure ArcGIS to help you determine the optimal size of your bandwidth in order to get you the best models. So essentially, you can think of the AICC as another measure similar to the R² value. So what they're trying to do is they determine the bandwidth in order to increase or maximum your model performance at each location. So that's what they're trying to do. Even though you might argue, kind of the optimal models, it is not necessarily the most useful models. However, in this particular application, it could be the way of, helping you easily find out the best fit models for each location. So I think for now, especially for this class and also for the the final project, feel free to use adaptive in addition to the AICC method to determine your kernel type and also your bandwidth method. So once you're done with running the model, you will get, because remember we saved our output into a shapefile, into a new file. So when you open the attribute table of the result file, you'll be seeing something like this. Because we mentioned every single location will have a different model, a different set of coefficient, and this is how the results are going to be organized. Here, because for each location, the same idea, each location is basically represented by each row in this attribute table. So for each location, we have a different set of intercept, coefficient for the population, coefficient for the low education, coefficient for the distance to urban center. So if you trace each one, you can definitely do, okay, I'm just maybe like looking at one particular feature and just write down all the coefficients. You can do that. But also, since so far we have been playing with spatial data a lot, I'm sure you folks can see that there is an opportunity to map your outcome, since we have different coefficients for the different locations. So that's actually what we're going to do for the lab, and also maybe for your simple analysis for the project. So the first example of the map I'm showing you folks is the slope coefficient of the population variable. So remember, each location will get a different coefficient for each variable. So basically, we have three variables in total: population, low education, and also the distance to urban center. So for each of the variables, each of the explanatory variables, you can make a map to show how the coefficient change across the study area. For example, here, and also actually when you work on the lab, you will see that I do recommend changing the color break a little bit, so that you can break the negative values and the positive values into two different color schemes, and so that you can observe the difference a little better. But in some cases, you don't necessarily always have some negative and some positive. In some cases, you will only have positive, and in that case, you can use a range of red. Or if you only have negative, in that case, you just only use the blue hues from light to dark. So in this case, you can see there are several blue locations, blue census tracts in Portland. And those are the only locations with a negative relationship between your Netherlands cows and your population variable. So that's actually interesting, because remember, when we run the global model, the population variable was only positive, right? Because for the global model, you can get only one slope coefficient for each variable. And that was positive, and that was exactly what we expected, because we do expect when there are more people, there will be more Netherlands cows with more incidence and all this related features. But in this case, if we run a GWR and we fit a different model across each location, and we can see it's actually not the case. And there are a few locations we do see negative relationship between population and and Netherlands costs. And then if you basically, you'll be based on your empirical knowledge about the study area, you can just keep digging into what is happening there. Maybe there are some other factors explaining why there's a negative relationship between population and the Netherlands costs at certain locations. And also, for the majority of the rice in the study area, the census tracts, majority of the rice census tracts has a positive relationship between population and Netherlands costs. And also color-wise, let's make sure to use darker color for higher absolute coefficients. For example, if you have a large range of negative coefficients, definitely you want to use the darker blue for the low negative coefficient or the highest absolute values of the coefficient. And in general, like here, because we didn't really look into what is happening in the case of Portland, but in general, there are some recommendations about how do you rate the coefficient from GWR. First of all, sometimes you may see a variable is statistically significant with the global model. And however, when you run the GWR, you see, locally, they're not that different. So in that case, it could indicate that the global model works fine, and you can implement some regional, basically regional means the whole study area, some regional strategies for the whole study area. But also in some other cases, maybe you do have significant variables, but you also see the strong regional variation. So in this case, if you do see the changing of relationships across your study area, the next step might be looking into what is going on with the negative locations. So does that make sense? Or would that be better if you kind of run the model again without looking at the specific locations? So those are some interesting indicators of, what is really going on in your study area. So that will, the local version of the model will give you some idea on that. And also, remember, sometimes your global model may not be significant. Like in that case, we mentioned you can remove that model. You can remove that variable simply. For example, if you run a model and you plug in employment in the Netherlands cause case, and somehow your employment data isn't significant, you can simply remove that variable for sure. However, if you maybe just keep trying and run a GWR, you may see, the reason why the variable isn't significant globally, that's actually because the same variable actually has changing relationships with a dependent variable across your study area. Maybe say in the west side of your study area, it shows negative, but on the east side, somehow it shows a different trend. So that can be some indicators of, how do you handle things moving on. You can maybe separate your data and see whether the spatial trends, the variation makes sense to you. So again, I think just basically the GWR will give you a lot of new information, and also it kind of actually will introduce some new questions as well, because based on your GWR results, you will likely see there are some more questions to be answered, like how do you deal with the spatial variation? Instead of just simply removing a variable, you can see if there are ways you can maybe take some subset within your data and rerun the model again and see if that changes your results. And feel free to let me know if you have any questions, because the GWR part is also, again, a bit different, because we're fitting a different model at each location. And also, you can definitely map the coefficients for each variable, but also you can map the local R² value from GWR. Because each location has a different model. A different model will have a different coefficient of determination. So basically the model performance can be different. So in that case, if you look at the local R² value, recall that the global model has a R² value about 74%, 0.74. But if you look at the local, of course, there's going to be a range of values, and it ranges almost from 0 to 0.93. So the highest location really has very high R² value. So in this case, if we use darker color for the higher R² value, you can see this is actually the downtown location. The downtown locations has the highest model performance R² value. So, they're basically between 0. You can change the break values to, to something that makes more sense. But also you can see there are some locations on the west side, the model didn't perform well. It's only like about 10%, less than 10% of variation being explained. So that can also be an indicator of maybe you can try to think of some variables that can capture the difference between what's going on in this western census tracts versus the rest of the study area. And also, I do want to just clarify that the local GWR, because basically you're fitting a different model at each location. The local GWR will always, if you're looking at the highest R-squared value is always going to be higher than the global, because the global is pretty much like an average. Although it's not really like you calculate the average, but it's more the idea is the global model is a representation of the average for the local models. So there are usually, of course, some lower R-squared value, but also some higher R-squared value. And also the whole point of fitting the GWR is not to achieve high R-squared value. So, I've seen this mistake very common that people are stating that, okay, GWR give me higher R-squared value, so that means my model performs well. But, that's really not the use of GWR, because your GWR will always be better than your global model. And that's the nature of GWR. And instead, the use of GWR is for you to figure out what is going on spatially. The reason why you want to run GWR is you want to figure out how your trend is changing spatially, or maybe you're missing some variables. So it's just more like basically, based on the GWR results, you want to be able to say, there are something that I'm capturing with my model, but maybe I'm missing a certain variable. You can use this information to further refine your model, or you can actually draw some conclusions from this model as well. Maybe you see in the downtown area, certain variables are important, but you see a different trend. So that will give you ideas on implementing different strategies across your study area. So please keep in mind, our goal is never to achieve higher R-squared value with GWR, because it's always going to give us higher R-squared value. Actually in the lab, you folks will be, as part of the results from GWR, you will be mapping the slope coefficients. You will also be mapping the local R-squared value and, briefly interpret your results. I think, like if you're just wondering how this works, once you're in ArcGIS, you will just quickly see, basically you're just like mapping other variables, mapping income, for example, but in this case, you're just mapping the coefficient or mapping the local R-squared value for each location. And, be careful when you apply colors, make sure you always use darker color for higher values, which should, help people read your map easily. And also, I do have some final comments related to GWR. So under today's D2L, the section, I have an optional material that I've just posted today. You can save it for future reference. So it's pretty much like a whole document as cut to the GWR handbook. They discussed some of the major issues and critiques on GWR. So actually, it's recommended that we only use GWR as an exploratory tool, as opposed to like doing prediction or drawing a formal conclusion. So actually, if you do some research on GWR, and it's mostly for the graduate students who are thinking about using regression, you'll see there are actually a large group of scholars who who do not like GWR for formal use. And there are, basically the issues are discussed in the handbook. And essentially, because GWR is more about picking the local values and fit a local model, especially it's not recommended for prediction purposes, because, you're basically picking the values that is going to benefit a higher performance model. But also, personally, I do like the use of GWR for exploring the spatial variations, because for geographers, I think the most interesting thing is about how things change spatially. And that can be really powerful for us to get information. For example, you can use GWR to help figure out what variable is missing and to further refine your OLS. And also, there are some new creative uses of GWR. For example, I can talk about the idea, but I will probably have to find the article and send it to you later. So recently, because I've been doing a research on urban pattern analysis, and the great news I found out through doing this article review is I saw the increasing popularity of spatial statistics in research use. There are really a lot of people applying the pattern analysis, cluster analysis, and trying to identify, for example, urban centers from satellite imagery, or doing some identifications on, the POI data or the social media data in order to, analyze maybe urbanization or gentrification or some issues in, the declining cities about urban shrinkage. So recently I found an article, they're using GWR to help identify the urban centers. So basically they're trying to do some analysis on urban morphology and trying to determine if a city is going more towards monocentric or polycentric. So, the difference, monocentric model, urban area is only one center and you just keep expanding, but there's only one key core urban center. However, there's also this polycentric model, which is actually becoming more popular. And actually, that's what the research found out, that most of the cities they have tested, they all expressed a polycentric pattern over time. They found out more urban centers. So in this particular case, they applied the GWR to look at the local activities and fitting the models through satellite imagery and other related variables. Yeah, I'll be sure to, I think I found that article here. Yeah, let me just make sure to send you the article. Maybe I'll put it in the course library folder under D2L. And there are some similar applications of GWR, by bringing in satellite imagery data and some big data. So speaking of big data, social media data, and also, like the search engine data, POI data. And there are also sometimes you can do on your phone, some apps allows you to do a check-in, so that some of them are POI check-in data. And also just, come back and, there are some issues and some, additional information we have to explore. But for this class, 3 things, of course, first of all, how to run GWR in ArcGIS. That's easy. That's pretty much, you just plug in the program, and the settings is always pretty much we can use the same settings throughout the different work. And second, how to map and also interpret, how the different coefficients of explanatory variables change across your study area. Basically you see some positive relationships, you see some negative relationships, and why is this happening? How does the trend change? And also third, how to map and interpret how the local R-squared value vary across space. There are some places you see the model fitted really well, but also, clearly there are some locations the model doesn't perform well. There's only like 10% of variation being explained. So what is going on? Really, like what is missing there? What do we not catch through the different variables included in the model? So for now, especially for Lab 8, I would say, it's not necessary for you to get a best model. You can just, just pick 4 variables and get your model, and make sure you know how to interpret your results. For Lab 8, because I got some questions from you folks, for Lab 8, it's not required to refine your model because there's no end. You probably can spend the rest of the semester just to refine your model. So just leave it, whatever variable you chose, interpret your results, and should be fine for now. Okay. So any questions on GWR? And we have a lab work day on Wednesday. So we'll continue working on Lab 8. The second part is the GWR. And I do have a few things on the final project I want to remind you or want to just, get some feedback. So we're going to spend the 2 days next week to work on the project. I know many of you are working, well, basically working on this project independently. So, I'm assuming there will be some more questions and discussion on, like choosing the methodology. And also at this point, I do recommend if you haven't got any ideas, I would recommend going with the existing options on D2L just to save time. You can get their data and just start, get familiarized, basically look at the data structure and so that you're ready to go on Monday next week. Okay, so, let me know if you have any questions and I will just go over the final project plan. So we're going to do 2 work days next week on Zoom. So, basically it's like a regular class, but instead of giving you folks a presentation or discussion on anything, we'll just jump right into, the work time. And I think only Andrew and Simone are working together. So I will basically put you two in a breakout room. And I may also set up additional breakout rooms, just for those of you who wants to maybe, even if you all work on different things, but you can still, maybe just get an idea from each other of, like, what do you think of using a hotspot analysis here? Just, get some validation about your methodology so that you can be more confident. And of course, I'm happy to, if you want to send me a quick idea on your topic, your data, and then 3 methods, 3 statistical methods you want to choose, I can give you some feedback as well. So that's the workday plan for next week. And demonstrations or the presentations will happen on basically the following Monday and Wednesday. And I put tentative here. So I basically had the schedule in the syllabus. And this time we're going to have 14 presentations in total. So I'm thinking, I think it still probably makes more sense to do the breakout room presentations as opposed to like we just, everyone has only 10 minutes to go over everything. I think that's just really gonna rush a lot and we don't have time for discussion. So my idea is we're going to use the 2 days to do the breakout room discussion presentation. So you're basically presenting within your breakout room, and so that you can have some conversation, and also we can do the anonymous feedback form. So I'll be using a Google form for you to provide feedback. If there are additional things you don't want to suggest in person, in front of the people, you can give them feedback. And that's also the form I will be using. I'll go through your slides and give you suggestions. So that's my idea, but also there are, I think we have some flexibilities, although that would really squeeze the presentation time. But I will ask for your, I think we can talk next Wednesday. So there's a possibility that we turn that Monday, November the 30th, into another workday, depending on your progress. There's a possibility, but also I want you folks to try to get, just work ahead of the time so that, that actual one day, I just hope that can, because it's still around Thanksgiving, even though your parties are canceled, but I think it's still going to be different. Maybe you want to use the time to relax. So there's a possibility we can use the 30th as an additional workday, and then we just somehow do a shorter version of the demonstration on the December the 2nd, which will work. It's probably just we won't have time to go over everyone's presentation. So you may, like within your breakout room, you can hear 3 to 4 presentations, and you can go over as many as you can. But of course, if you're willing to go over all the 14 presentations, you're welcome to do so. I think it will be rewarding that you can really see how different people are approaching the questions differently. And also I posted a template, presentation template, which is a PowerPoint file on D2L. You don't have to use my template. It's just an idea of, it's kind of a reminder of the structure, what you need to include in your presentation and also in your paper. So feel free just to grab the template if you don't mind about the design, because there's no design, it's only black and white, black background and with some text. But I guess you can change the design as you want. Let me see. Oh yeah, so to respond to Amy's question, so I'm still planning to collect all the presentation slides through a Google Drive before class, so that we all have access to all the presentations, and you're free to take a look before class even, and I will leave them open so that we all have access to the different presentations. So if say somehow in class you're only able to go over 7 presentations, you will still have time. If you're willing to spend extra time to go over the other 7 presentations, you're free to do so. And personally, I will go over all the 14 presentations for sure and let you know any critical issues before you submit your final report. So the presentation definitely matters, but also I will weight your final report higher. So, like when I read your final report, I'm looking for whether you're responding to the critical feedback. So my feedback will be embedded as part of the anonymous feedback. But usually, I think you can trust your classmates for their, the issues they brought up. So usually, before I put into anything, I usually found the comments I had that has already been mentioned by someone else. So personally, if you're new to this breakout room based presentations, I would say, there isn't much difference. It's just only that it's less formal, so you can be more relaxed with your presentation. And also, I can assure you that you will get better quality feedback before you finalize your work. So far, it has been working out very well. And also, we just make sure to give each other very constructive suggestions, something they can quickly apply and work instead of asking people to try something entirely different. So that's just something we can keep in mind, and I'm sure it will work out well. And the final report will be due on Saturday. So that'll be September the 5th. And, we still have a final exam, same structure afterwards. That will be due the Thursday, the following week. So I think there will be a reason why you want to get your reports done earlier so that you can focus on the final exam. So yeah, I think also that Thursday not that Thursday, I think, that's actually a Monday. The following Monday after, after the presentation week, I will still host a Zoom session. So, if you have any questions on the exam, we still have one day to check in. And of course, I'll be available via email, and also, you can reach out to me. We can set up a Zoom meeting. So you can ask questions on the practical portion. You can ask me to clarify on things. So yeah, that's the plan for the rest of the semester. So mostly work, but I'll be here to support you. But also, I think, as far as for time management, that's something we all have to work on, because I know it's tricky to just kind of follow the schedule and get work done on time. But at this point, let's just make sure if you have any questions, don't wait. Because if you're trying to wait one day, then that's just maybe it will take a few more days. So just try to get things done on time early, and so that we have time to, and also I'm sure you all have other things to take care of, other classes and other duties.